So welcome back, and this is going to be the last lecture, so to speak, last part of the last lecture. In this half an hour, 45 minutes or so, we will actually discuss something that everybody should pay attention. Right? It has wonderful history, and then basically currently a lot of practice, and there are multiple groups working independently, and then not enough collaboration is happening, and some collaboration is happening. There are a lot of stuff going on in this area, to say the least, right? And the first thing that I want to talk about is a very general discussion of something called a neural network, and I hope you already heard about it. I think there are enough students, mostly people taking course on neural networks for various purposes. In here I'm going to speak specifically from the perspective of control systems. Yeah, so neural network is not a new idea. It started back in late 60s, 1960s or so, and it started as an idea to model how our brain works and things like that. And sooner or later, basically, the assumption that we are actually modeling brain has gone away, and then basically they accepted that the brain is a lot more complicated and we may not understand anytime soon. A lot of cognitive science that is happening these days still borrows ideas from neural networks, but they're not trying to at least put a simple model for the brain, right? Instead, basically the work on neural networks became what we call as artificial neural networks, only for sake of computation, right? And the idea is something like this. I'm going to at a very high level. Let's say I have some vector u and then vector y, and then one is called input and the other one is called output. So u1, u2, and so on and so forth, y1, y2, and so forth, right? And I want to understand the connection between u and y. And let's suppose y is equal to f of u, right? Let's even suppose that f is given, and perhaps it's not in a really great form and things like that, or maybe it's very difficult to compute and things like that, right? So the idea of neural network is basically, so can we actually get some kind of standard framework to approximate this f using some universal functions that are put in the format of neural network. And in a second I'll explain why we actually don't typically assume that we know this particular function. And I'm going to connect. Okay. Let me put some intermediate nodes here. Let's say I'm going to connect each one of these nodes to these intermediate nodes, and then these are connected further to every one of these things, right? Don't worry too much about what they mean. I'll explain in a second. So every time you see a line connecting two things, basically this is essentially, this is going to be summation of all weights multiplied by the corresponding input. So if I call this as z or something like that, z is summation of all the nodes, all the arrows that is coming here, and then each one of those edges have some kind of weightage, and then there's an input corresponding to each one of those edges, and you take a linear combination with respect to these weights, right? And then take these z's, and then again they become inputs to these y's, right? And you can imagine we can have hundreds of such intermediary stages and things like that. Yeah, so you can have many such intermediate, the word used is actually layer. Each of these things is called a layer, and the terminology may have each of those things as neurons and whatnot, but as far as the mathematics is concerned, basically y is a linear combination of all previous layer inputs, and each of those layers is a linear combination. Actually, no, I should be careful. Z is actually the weighted some kind of nonlinear function. So I keep saying it's a linear combination of nonlinear functions of all its inputs and things like that, right? Z1 is linear combination of some function that multiplies operates on each of the inputs, right? And this f, designing this f itself is a open problem for the longest time, and then basically eventually they came up with certain functions that work very well and things like that. Okay, this f and this f are not the same thing. Anyway, so essentially y is linear combination of let's say wij some f of its layer inputs, and then each of these things again linear combination of these nonlinear functions of its own inputs, right? So you essentially have lots of these weights from each edges, and then each of those weights are going to multiply this nonlinear function and then finally give you this y, right? The theory is basically let me use capital F to distinguish between this small f and this thing. So the theory basically eventually people figured out that any function capital F can approximate through this neural network, right? So you can always find a neural network that approximates this very complicated, possibly complicated function f very closely, right? And that's called the universal approximation of neural networks. Now, what after that? Well, how do we find these weights? So that's where a lot of research, initial research of neural networks went, and then they discovered something called backpropagation algorithm, and then it's essentially based on gradient approaches where they minimize the errors between what is supposed to come from the actual, you can give some inputs u1, u2 and things like that and get some outputs, and then use that information and then essentially do least square estimation for each of these weights. So more amount of data you have for u and y, basically you put in there and then try to find the best possible values of w1, w2 and things like that. And there are multiple things here. So let's say you have data of 1,000 points or 1,000,000 points. You cut into three different sets and take the first set to actually estimate the values of the best possible w1, w2, and then take it and test it on the second set, and then if it works, then that's good, and third set we can try it again, and and you can improve it on the second set if you want, and then keep iterating and things like that. So that's kind of offline training that we use to approximate some unknown function. Why unknown? I mean, here I'm assuming it's known, but in general, this function could be actually coming from a physical plant. You just have some inputs and outputs, and how do we connect them, right? And find the weights, and then hopefully the universal approximation theorem works, and then basically all these weights will be so optimal that this f of u is no different from this neural network, right? So obviously we don't want to apply to things where we know actually what is f. It's only useful where we don't know that. And we can do this offline training and get the w's. We can also do online training, basically where as and when the data keeps adding to this particular network, we can have an update for w1. This is something similar to what we did in your adaptive control, and in fact that's a very nice way of thinking about, let's say if you have something like f of x plus g of x times u, approximate this with neural network functions. So basically essentially you'll get bunch of wi's times known functions, call them h of x or something like that, and depending on how complicated the network, this could be double summation and things like that. You will have bunch of weights. The assumption is the weights are unknown, and then we can use basically this feedback control approach to actually estimate the values of weights, and then eventually also figure out an algorithm that forces x goes to 0. So let me summarize what I mean to say here. So suppose if we have the adaptive control idea that we proposed works when we have constant parameters. Now if we don't have the constant parameters, basically we going to replace this f of x with this bunch of parameters times this known functions of its own inputs through this neural network idea, and then you know, control for these parameters wi through this thing. Of course, we can also do the following. Instead of doing all these things, somehow if we knew that this is a controllable system, basically you know, you imagine that there is a phi of x that stabilizes, and phi of x is now estimated with a neural network, and then basically that's more the direct adaptive control idea, and then find an estimate for wi, right? So and the gap between phi of x and this one sometimes can kill you, and it may not exactly send you to the equilibrium point, but actually may work very well in many times in terms of sending very close to the equilibrium point, right? So so in that sense, neural network ideas are fairly useful in controls if we know what exactly we are talking about. And this perhaps if you are interested, you'll find keywords like adaptive neural networks or adaptive neurocontrol and things like that, right? So that's one idea that's good to know. And the second thing that I had in my list of topics is basically something called data-driven approach, right? I'm not going to really spend a lot on this basically, but essentially what this is saying is, you know, if we don't have a model, then all we have is a model. Then should we really work hard towards actually figuring out a model and then use that model to control, right? And that question is very, very important, simply because all the information is available in data, and if data is what we are using to approximate the model, then why should we not directly do everything with data? So that's called data-driven approach, so that we don't ever have to do an intermediate step of modeling, right? Let us understand very clearly, you know, I think it's philosophically, suppose when Newton, for example, developed his gravitational theory and things like that, it is observation of a lot of data. There's no doubt about it. But and then it is one thing, basically, somebody like his predecessors, like Kepler and them observing certain phenomena by looking at a lot of data. You'll only see always discrete data, but then you suddenly see some ellipse emerging from this discrete data, and then putting some theory that, okay, this ellipse is because of certain things. And then further Newton comes along and basically, okay, no, this can be explained because it, you know, the gravitation is satisfies certain inverse square law and things like that. And of course, then basically it's a human ingenuity on his part, and others, other great physicists around that time, to extend that notion to the entire universe and things like that, and then treat a small apple and a planet at the same way using the universal gravitational law, and then that's really fantastic. So from a data science perspective, you're still relying on data, and then generalize that through some kind of approximation of some ellipse or inverse square law and things like that. But to realize that it actually applies to planet and apple is something only at this time only human can do. Perhaps the AI models too soon can do such things. But in all this, basically, if you don't have such first principles based on large amount of data collected over centuries, perhaps, what is the approach that we follow? Today we follow, basically, we curve fit that particular data to something, and then use that model as if it is you know, very sacred, and then design controllers and thinking that this is the exact approach and things like that. So the approach of data-driven people is basically, why not use directly data to control rather than using this intermediate step? And you know, if somehow you knew these linear systems, I mean, if you knew somehow this system is linear, then things become somewhat simpler to understand and design these data-driven controllers. You know, I'll explain this in continuous time, but it's typically implemented in discrete time, and then similar approach can be done in discrete time. So we know that basically the solution to this is e raised to a t x0 plus integral e raised to t minus tau b u of tau d tau or something like that, right? So we know this. So for certain constant u's and things like that, we can actually write this very carefully, and in discrete time, basically this becomes a bunch of products of A, powers of A and things like that. So if you want to go from one particular x0 to another one, we can actually figure out what should be u and things like that. So that is the standard control approach. But that u, in the continuous time, it depends on certain data available directly in the raw form of data, and then why not use? So essentially you express u directly in terms of a x1, a x2, where x1, x2, x3 are all in the discrete time sense, basically the values at a particular time and things like that. So you collect the data over particular time. This, as I said, typically implemented in discrete systems, and works out very well for discrete systems. You collect the data over certain number of periods, and then put them in a certain format, do some magic with it, and then provide that to you, right? So one simple logic is basically the observability and controllability grammene. So basically, essentially, you pick this y dot and things like that, put them in a format. That is invertible. We can get back the state from observable y, and that's observability grammene. And similarly, we have the controllability grammene, and then we can develop formulas. So essentially, we have those formulas, and then we use those formulas directly, and then implement on the data, right? So that is data-driven approach, and then a lot of work that is going on over the last I don't know, 5-10 years perhaps, and then it's still continuing to happen. I keep seeing papers on different types of data-driven control approaches, with uncertainty, without uncertainty, for nonlinear systems, cascade systems, all kinds of systems. So if you're interested in pursuing a modern topic of research, then data-driven approach is something we should consider, right? So so that brings us to a topic that some of the control engineers started to look at, and then they have looked at it quite carefully. It's not something new. Over the last 20-25 years, people have been working on these topics from our controls community. Is basically something to do with learning approaches, and people now in computer science and other fields are obsessed with this particular approach. And then of course we have gone way ahead in terms of creating these algorithms that can produce text. I'm sure you're familiar with ChatGPT and large language models and things like that, where somehow you make the machine treat the entire language as, to put it bluntly, as a neural network model, and you give input some specific sentence, and it can actually guess what should be the response and things like that, right? So so you ask ChatGPT to basically rephrase some paragraph. It actually knows exactly what it should be through its own neural network, or the learning model that it has inside, right? So in a way, if you translate that into control systems, basically, can we make machines learn by knowing all the inputs and by knowing the goals in terms of trying to stabilize or converge to some particular point? Can we actually estimate the value of u? In a way, it's adaptive control, learning to estimate certain parameters, but adaptive control is very restrictive in terms of identifying parameters that are constants, and we have stability proofs for those. The extension that we just pointed out is using neural networks through this weights being the constant parameters in the adaptive control framework. Now we are talking about, can we actually use the general machine learning framework with a similar kind of approach, where we kind of trying to learn the entire system through some internal neural network model, and then we don't really need to know the details in terms of the neural network, but we somehow figure out to optimize over the controller, right? So that's essentially what is machine learning, from a controls perspective. But there are some really fundamental questions that come into picture. So one of the things that earlier when I was discussing neural networks, you have some kind of u, you have some kind of y. If we have a static function, that can be approximated using universal approximation theorem of neural networks. But if it is a dynamical system, how do we handle that? Well, there are different kinds of neural networks that can handle actually time as also one of the parameters, so we actually get time as a solution. But the question is basically, do you just get f of t comma x comma u question mark, what is x here, or perhaps you only get in terms of f of t comma u. Is this enough? Does this have memory? Whenever you have a dynamical system, when we solve it, it tends to have a memory. Perhaps you can have another parameter including some initial condition and things like that. So all those questions will come into picture, but there are different types of networks that can handle dynamical systems. Specifically, they are called as RNNs. I'm throwing out a lot of terminology without really going to details. Recurrent neural networks are supposed to be ideal to approximate dynamical systems. And what after that? Okay. So these are in general called as model free, and I have part hesitation to call them as such, model free approaches. I mean, I'll explain the reason why they are called model free, and then why I hesitate to call them model free, and then where is the resolution to these questions. Anyway, so once we have this approximation of this G in terms of a neural network, and then perhaps we hope to learn from that neural network. I mean, whenever we approximate some system from basically based on input output data, we don't have the actual simple form of G, so we use this neural network and recurrent neural networks to get a neural network version of this particular system, right? Of course, typically we don't care for that kind of approach just to understand the system. Typically what we want to do is, we have this G, we want to control through some dynamic controller. We have inputs, outputs, perhaps in a negative feedback. And what we can do is, let's say if we are doing an offline approach, we are going to basically approximate this with some neural network, again perhaps a recurrent neural network, so that it has these memories and things like that, and run through the system. You collect the inputs and outputs, and then keep updating your weights in this particular G sub C, and hopefully eventually this becomes a stabilizing controller, right? So how to train these W1s, W2s, not just to approximate Y and U, but actually we want to force the Y to be going to 0 and things like that, right? So by the way, these days there are many advances in neural networks. One of them is basically physical they're called pins, P-I-N-N, right? Of course, NN is neural network. Certainly I forget what is I, but physically I think inspired, yeah. So physically inspired neural networks, which essentially are the neural networks of the general kind that we've been talking about, except basically, suppose if you are dealing with a physical system where energy is constant, let's say, right? So you can actually have a energy function there as part of your weight updates, so that weight update satisfies that constraint. So in other words, basically these are like neural networks that satisfy certain constraints. There's nothing otherwise so great about them from a conceptual perspective, right? From an algorithm perspective, it's not that easy. So people actually discovered, invented basically many algorithms where they have these neural networks that are physically inspired. So that's in a way, instead of just using raw data and just not worry about some of these physical aspects, we can actually put these constraints, and then that constraints are good to know, and that helps us designing controllers. We can impose constraints and things like that. Now, why are they called model free approaches? They are called model free approaches because of the fact that, yeah, so they are called model free approaches for one single reason, that the model that we rely on, which is a recurrent neural network or some version of that, is so complicated that it's essentially useless model, right? So but of course the fact that we actually are designing controllers just based on input output data without ever really invoking the information that is of the plant. I mean, it's not coming from first principles and things like that. So we can treat this as if we are designing controllers without really getting a lot of information of the form of the model, right? So but then you do have a model, you are actually designing a controller of certain length and things like that, right? I mean, one of the things that I didn't really really talk a lot about is in the 70s these neural networks discovered or invented. Basically, it's slowly a lot of work was done in terms of how to design these weights and things like that. A lot of algorithms till about 90s, mid 90s or so, people discovered that they're too difficult to apply to most of the cases. You need large amount of data, large amount of computing power, and they gave up. And perhaps about 15 years later, the computer power is so much, the memory as well as computing ability, people started using neural networks. Now they're everywhere, and not just neural networks, and all kinds of different frameworks are there to solve these kinds of problems. And then basically it now becomes a very standard thing to use neural networks as part of this, right? So now we can actually solve very difficult problem through this approach, and in some sense you only need input output data, not much information is needed about the plant, so therefore they are called model free. But there is a model, right? But it's useless because we can't really say much about it looking at the model. And then again people start talking about explainable neural networks or explainable artificial intelligence and things like that. It approximates some unknown system, but can we understand through this approximation what this is supposed to be doing, right? Eventually humans are obsessed with trying to understand what is going on, and let's say in our case we are obsessed whether this is provably stable and things like that. So that brings us to the last thing that I want to say before I close the course, so to speak. In all this, let's say we accept this model free approach. We have some input output, and we design these controllers based on this neural network. The neural network itself, even in the recurrent case, perhaps we can think of this as a differential equation or a difference equation. So we have the concept of state and things like that. But it's so complicated, it's useless in terms of defining our stability and things like that. But we actually did not touch the plant that we are trying to control. We are only talking about the neural network problem for approximation for the controller. So we don't know anything about the plant itself. So is there a need for definition of state? Can we just live with input and output? Now, to the best of my knowledge, if you actually have a description of the input and output map in some fashion, if else the rules and anything, we can actually associate a state with it. We have worked on things like hysteresis, time delays. In every one of those things we can actually associate a state with any complex operators. I mean, the operators like time delay or hysteresis are relatively straightforward, but the point is they serve as an examples where we can always find some state, and those states sometimes are infinite dimensional, sometimes they are finite dimensional, and and therefore appropriately we can actually define stability and things like that. But here we throw away the notion of stability. We are just interested in u and y and things like that. So the fundamental question remains is basically, do we actually need the concept of state, which this entire course is dependent on? But of course, more fundamentally, the question therefore becomes, why did we define state and why did we define equilibrium and instability and things like that? Is basically to make sure that our systems are safe and sound. Here, what kind of guarantees can we get, right? And there are no answers at this point. The guarantees that a very high level we can actually guarantee that from an input-output map perspective something can happen, but whether these inputs and outputs capture the entire state or not is a question that is not addressed by the model-free approaches, and then that remains open as far as I'm concerned. And a lot more can be done. I mean, all these things put together, basically the dynamic programming principle that we were talking about was used to discover many algorithms, and they're called reinforcement learning algorithms. And and they work very well for control systems, especially optimal control is best solved using reinforcement learning algorithms. And all these approaches are best used, of course, for systems where we have no clue, or even if we have a clue, something like an airplane, I somehow theoretically convince myself that I know how to control this particular system. It's just that how to find the answer for that controller, specific controller, may be difficult, and that will lead to safety. So I have an answer that there is an answer. I have somehow convince myself there is an answer to this particular optimal control problem, and neural networks can actually then becomes essentially a computational method to search for that optimal control through reinforcement learning algorithms or whatnot. So all I can say is basically if you're applying to completely new problem and we have no clue whether this particular problem is has a state or not, and then whether there is an equilibrium or not, whether this particular implementation will lead to safety, safe closed system, then we are risking in many ways, and then those questions are not answered. But if we have some other theory to support that we can solve this problem through traditional methods, it's just that traditional methods only tell us existence. It's like basically Lyapunov functions. We know that there is a Lyapunov function for every stable system. Now we can search using sum of squares approach and things like that. So similarly, if we know that there is a controller, like in a helicopter, there is a method. These inputs and outputs are useful to control that particular system and keep it safe. It's a matter of searching for the best possible control law through these learning algorithms, and specifically reinforcement learning is one of the best methods. And so basically, if somebody is interested in machine learning, certainly learn basics of machine learning, but eventually one has to understand reinforcement learning algorithms. And these days, if you want to just understand how to implement them, MATLAB reinforcement learning toolbox is quite straightforward to understand how to implement on even a very generic control problem. But they have different what do you call different methods, different let me put it in this way, basically different costs to be minimized and things like that, and then each approach will give a different answer, and then one has to learn enough to figure out which one is best. But that's a practical way of doing it. If you want to understand more mathematics behind it, there are a bunch of books, and one of the first books that I came across is a book by Bertsekas, and there are several other books, but Bertsekas gives us a very nice control approach to reinforcement learning algorithms, and it's in fact, he initially called it, I believe, reinforcement learning, or I'm not sure, but I think eventually the term that Bertsekas uses is something like neurodynamic programming. So the word programming is in the sense of optimization, and neurodynamic is basically using some neural network ideas. So neurodynamic programming is where we can optimize systems based on neural network ideas, right? So I do not think that any control engineer can survive these days without knowing anything about machine learning approaches or model-free approaches, or specifically reinforcement learning control approaches. So those of you who are looking forward to a more advanced courses on these things, like I said, certainly consider something on differential geometric methods, study on your own things like hybrid systems, machine learning in general, and then of course reinforcement learning. Things like model predictive control does not require an entire course, but perhaps there are those courses where you see applied nature of such methods. All these are possible, and wish you all the best. Thank you.